So Abaqus CAE. So what is the full form of CAE? Can anybody tell me what is the full form of CAE? Let's begin. CAE is computer aided engineering. Okay, CAD is computer aided drawing or drafting. CAM is computer aided manufacturing, and CIM is computer integrated manufacturing. So everybody is screen is visible for everyone, and my voice is also visible. I hope audible. Sorry, everybody can see the screen. Yes or no?
Yes, sir.
Yes. Okay. So let us just continue. So now this is the typical. I thought somebody is joining. I have to re-come over here and enable people to join. So this is a typical Abaqus CAE 2020 viewport. Viewport means your. This is. So now you can see over here that this is the basic model. This is the system which is there in everyone. Then these are some of the basic uh, model, wireframe model, hidden model, shaded model, and then this is for showing the mesh system and everything. And the basic thing we have to see over here is two things. The first one is the model over here, and the second one is the result. So once you run the program and your simulation is working, and then it is showing the result, this is where you will get the result. So you can see in the previous session also somebody asked me that whether we can plot it the data or not. So you can see this XY plot is there, XY data is there. Then this is the color coding. So we have not. Yes, somebody has raised hand. Okay, that by mistake, I guess. So, so this is where we get the all the results, and then you can make the movie also of your uh, simulation or of your results, and then you can get the image of it. So this is the basic interface. In the model interface, this is all what is. So we'll one by one we will see all what this is, and this is called module. So module, you basically have how many? 9 modules: part, property, assembly, step, interaction, load, mesh, optimization, job, visualization, and sketch. So this is the module. So the first step, first you go about is to make a model. So you can do two things. Either you can make a model. If you click over here, it will show create. So this is something which I have already told in the last class, that if you click over here, it will show create, or it will also show import. So if you have already made a geometry from the previous from any software, and AutoCAD, CATIA, or HyperMesh, Unigraphics, or any other software, and you have that geometry in the model, so you basically don't have to model this the geometry here. You can directly create on the import part, and you can import the geometry from where you have created, and the geometry will directly come on in the system. So that is one of the question which one of the guy has actually asked in the last class. So now we don't have any geometry, so we have to prepare the geometry. So there are different ways to prepare geometry. So let us just start, and we'll click on create. So now here you can see three-dimensional, two-dimensional, axisymmetric. So you have to understand each. What is three-dimensional? Suppose you are making a geometry in three-dimensional. So if you are making a geometry in three-dimensional, you have extrusion, revolution, sweep. This is a basic CAD thing which you might have done over there in the previous classes. If you are making a geometry in two-dimensional, you can see now there is no extrusion, There is no revolution, there is no sweep option coming. So okay, people are joining by themselves. Fine. So there is no sweep option. No such options are actually coming in the three-dimensional and sorry, in the two-dimensional, because you are having just a two-dimensional geometry, just like a rectangle or a solid or a circle or something like that, where you have only two-dimensional, the x dimensions and the y dimensions. So therefore, you don't need to make a solid body. Therefore, there won't be. So these things which comes when you need to make a solid body, you need to do this thing. Okay, and you'll have the two-dimensional geometry. So I'll give the example of each. So let us just suppose that we are to make a tensile simple way of making a tensile simple. So I'll choose three-dimensional geometry. Okay, and then again this is a deformable, discrete, rigid. Deformable means something which can deform, and discrete, rigid means something which can not get deformed. Okay, so you then here you have the shape. What kind of shape you want? You want a solid. So if we go to a 2D planar, you can see you don't have those shape. Here you have on shell, wire and point, and in 3D you have solid, shell, wire and point. So of course three-dimensional geometries are solid geometries, where in finite element simulation that is called solid, and two-dimensional geometry in the finite element simulation terminology, that is called shell model. And of course you can create a wireframe model that you should study in your CAD CAM and everything. So these are the two terminologies you have to understand. You can still have shell model in three-dimensional, but generally when people use three-dimensional, they use for solid model, not for the shell model. So shell model, what is the difference between the solid and the shell model? That solid model, if you want to know three-dimensional analysis, length, breadth, and height, everywhere, all the things, then you have to use a solid model. And if you want to do a two-dimensional analysis, then you can use a shell model. So first of all, let us just try to create a solid model. So we'll have this deformable solid extrusion, and then we will put on continue. Okay, and this is the approximate size. What is the approximate size? 200 means the mesh size. Let us decrease a bit and make it 100. Okay, so this is the size which we get. So now you can see over here that sketch the section for solid extrusion. So means you first have to draw a section. So there are various lines. You can see this as a single line uh, from here to here. Okay, this is a point. So you have to pick up a point. Okay, and then you can see this is a line. This is a rectangle. This is a rectangle which you have. You can draw three different rectangles. You can also draw over here. So all these things, basically, this is how you best draw the rectangles. Okay. So let's just go again to three-dimensional. So now we will draw. Let us draw. Try to draw a tensile sample. So you'll select this. There are various ways to draw a tensile sample, but you'll select this. You'll draw this. You will go here. Then you'll go here. I am just drawing it very roughly without sketching. Okay. Then you will have there. This is a this. Sorry. So now this. So this is sketch. This looks like a tensile sample, but one thing is missing. and that is the fillet. You we have to give fillet over here. So I click on this. This is a fillet part, and the fillet radius you can give. You can see over there bottom of the screen. That is where you have to give the fillet radius. So let's just suppose that I give a fillet radius of 2 2. Now you'll enter it. So now what it is asking, select the first entity near the end to be filleted. So suppose you want this to be fillet. This now it asking select the second entity near the end to be filleted. So you have to answer. So now you can see this is fillet. Similarly, you will do the fillet again in this one as long as you continue. So this is your typical
Uh,
sample.
Sir,
Yeah.
no need to check, sir. I am joining the people.
Okay, okay, okay,
Okay,
fine.
I'm also online. You continue your presentation.
Okay, okay. So this is how you join a fillet. So this is how you make a tensile sample now. Once you have done the filleting and everything, then you will see the dimensional. If you click over here, you will get a complete extruded part. But now you have to see the dimension. So dimension things can be seen here. If you want to remove any part, you can use. So first of all, let us go to add constraints. So add constraints. Now deliberately what I did is that I made this length. If you'll see, this length is starting from here to here, and this one is starting from here to here. So let us just try to make it equal length. So this is a rough. This is the rough part. Now you'll see over here, and you'll do this. Now this becomes this two has become of equal length. The length will be increased. Similarly, if you want to increase make the length of this two and here, then you do it done, and you can see that the dimension is changed. Dimension of this particular part. Similarly, let us try to do for this whether the length is same or not, and then you click on done. So now you can see that there is VV that is the same length. So this is how you do that, and then you can also translate the geometry. You can decide, you can move over there. This is the basic part of knowing the interface and everything. So select the entity to translate. So you will select the whole entity like this. This whole entity, this is red. Now that means your entity is selected. Okay, now you'll do done. Now pick a start position for the translation vector. So you can put the start position. Let's say our origin is our start position. Now pick an endpoint for the translation. So wherever you want to move this, you can move. Let us just pick an endpoint here. Now you can see this has been translated from here to here. Similarly, you can create the copy of it. If you see this, you can create the copy of it. Okay, select the entity to be created. Suppose you have multiple entities on your software, then you'll done. Then you'll have the start position here, and then you can have the end position here. So you can see that your two samples are created. Two tensile samples have been created. So this is I'm telling you about the interface and everything. Then you have the auto constraint option. Select the geometry to constraint. So you will select the geometry. Let us select this particular geometry now. So we'll do done. So now this geometry become the auto constraint. Auto constraints mean the software will automatically apply the constraints which are there to work up. Okay. Then you'll have the auto dimensioning part. So you can create the auto dimensioning from here. Then you can see the smart dimension, add dimensions. here. Now you let us suppose that you want to increase the length of it to 15. So the length of this is increased to 15. Now the interesting part is that you can see this length is increased when I have increased the length for this. But let us just try to see the length. Sorry. Let us just see the length for this. Select the entity dimension. The length of this is also increased. Why the length of this is increased? Because when we are doing this, uh, yeah, add constant. When we are doing the add constant part, so this particular part and this particular part, their length we have put as constant, equal length. Therefore, when I have increased the length for this, the length for this is automatically increased. Similarly, let us try to increase the length for this part. So this is 9.5. Let us try to do it for 15. And you can see this, that this particular length is increased to 15. However, these two lengths are decreased. Okay. This is very interesting. This length is decreased, but this length is not decreased because we have selected the equal length here and we have constant this one. However, for the top entity, we have not selected this. So you can see over there. Let us just look at this part, and you can see it is written over there V, and then there is a line. What does it mean? That V there is a line means that you have you have a equal length for this, and this is constant. However, in this you can see V, but you cannot see the cross line here. Therefore, this has to adjust for the removal. So this is what you have to do. Okay, this the dimensioning you can do over there. So auto dimensioning is done. Edit the dimension values. So this you can edit the dimensioning and everything. Okay, drag, add a sketch. Okay. So reset views. So you now you have reset the views. So again you have came to the original view what it was previously. Okay. Then you'll do the is sketch. It is showing sketch the section. So you sketch the section. Sketch the section for solid extrusion. So it will not happen. So now let us just this is for the CAD model. So we have had two sections over here. Okay, na. So now let us just redo and uh, redraw this and try to understand that how the extrusion part will look like. Okay. So let us just again do this, create 3D extrusion part here. So not this one. I'll not do fillet this time around. This is not two dimension. Okay. Now you can see that the part to be sketched. So we are giving the depth. So how much is the depth required? So you can give 5, 2, 3, whatever depth. Let us just give the depth 5. And then these are not required. So you do, and you have this sample. Okay. So this is still a very, very uh, big sample, and then you'll have to do certain things. You have to assign the section to it. you have to assign the properties. So there are many things over here. Assigning of the section, you'll go to the assigning of the section. So we'll understand this, or perhaps, yeah. So now we are selecting this. So this is a typical tensile sample, but the fillet I am not given for just to make you know what it is, right? So now you create the section, because now you have created the object in the space, but the software will not know what you have created. So you'll create the section, and on creating the section, you will have the homogeneous solid, because we have done it as a part of solid. So you'll have homogeneous solid and you will continue it. So now the software know. Now let us give the thickness here. So let us provide the thickness as 1.5, and let us do. So now you can see that it's showing missing values. Missing values means no material has been assigned to it. So now we go to the material domain. So we can also do this before. So before this section, I can cancel this section. No, and we can go to the material domain. Here in the material domain, you can write whatever the description you have to write. So let us write steel, low carbon alloyed. Okay. So what the material behavior. Now here you can see several things. There are many material properties which you have to put. Yeah, density. First thing first is density. So you have to define density 7.785000 in the unit. So you can see that density basically it's a temperature dependent data or not. So you are saying that, assuming that density is not a temperature dependent data. Then you have, I don't know what is this dependent variable. Okay, dependent variable. So you have to, so there are so many things which you have to, not everything is there. Then you also have the material which are fixed. So you can have your own user material over there. Okay, so you can have the user material, your material, you can give whatever constants you want. Then you have the user output variables. So this is, here you can see that you have the number of user defined variables at each material point. So you'll have user subroutine. What does user subroutine means? That it will have, so it will have the whole programming part. So subroutine means if you want to program something, if you want to write your own code, then you can write using the Fortran programming language which the Abaqus supports. Okay, so these are some of the density we have already put. So let us just move to the other part. Then the mechanical properties. So you have so many different mechanical properties which you can put. So let us see these many mechanical properties you have. If you are doing the vibration simulation, you can use damping properties, alpha, beta, whatever. Or if you are doing the fluid simulations, you can use the viscosity properties, dynamic viscosity, kinematic viscosities, and different viscosities. Then if you are using then if you are using the, first of all, let us just see, understand the elastic properties. So you have the elastic properties, you'll have simple Young modulus and Poisson ratios. Here it is mentioned no compression and no tension. So no compression, no tension means everything has to be same. Okay, and your properties will be Young modulus and Poisson ratio property will be same in compression as well as in tension. Then you will have the elasticity here. Then you'll have different kind of elasticity. One is the porous elastic model. So you'll have the porosity values over there. This is obtained using the tensile test and experimental values. So this you don't need to. Now go to the plasticity. So plasticity means you'll have to have the plastic deformation over there. So plastic deformation, something like you can say in the forming process, or you can say in the machining process where the metal cutting process where there's the plastic deformation thing is there. Okay, so that you have to put over there the plasticity property. So let us, you can see there are so many plasticity. If you are doing the concrete damage, so if you remember the previous session, so I have shown you that the crash analysis will be there. So car crash analysis. In the car crash analysis, what are the proper plastic properties you are going to give to the car material? And suppose that the crash analysis we are doing and the car is going and is hitting a ball, you can say a building. The car is stuck the building. So what is the property you are going to give to the car material in terms of uh, this? You will give
Mechanical property, that is toughness.
what?
Mechanical property, that is toughness.
No, that is your outcome. That is your outcome. Toughness is not your. You have to give the plastic properties, because the car when it's going to get stuck into it, it is going to show the plastic deformation, and you
Okay,
also
it will
have to
be resilience.
give the elastic property. So elastic property have to be given, because any property when any application happens, first of all we know the basic mechanics of it, that elastic deformation happens, and after that it goes to the plastic deformation. So therefore elastic properties will always be there. Then you will give the plastic property to the car. Okay, and then to the concrete you will give this property, concrete damage plasticity. So you'll have these properties, and these properties will be there for your system. uh, you will be supplied in the standard whatever the concrete you are missing and all. So these are the properties you will give to the wall. Okay, and then you'll have the cast iron plasticity, which is different to the normally the ductile materials. If you're using the cast iron application, but they are generally not used in the automobile. But if you are using the cast iron application, you will have this as a property. Okay, and then you'll have the plastic property down, and finally you'll have the porous metal plasticity. So porous metal plasticity, you'll have Q1, Q2, Q3. This is based on the ductile model, which you have to understand. And then you'll have the porous failure criteria. There you'll put some of the failure criteria. So that is we need to. So there's one GTN model. If you'll study over there, so this is kind of a model where, as I said, this is just one example of the model I am giving you so that you understand it. But similarly, there are many mathematical models. So this is how the mathematical model they have formulated, and they have Q1, Q2, Q3 over there as a constant, and then they have the F value. Then they have Fn value, and then they have Sn standard deviation value, and then they have the epsilon P and epsilon plastic strain and the strain at the mean effective strain. So these are the values. So let us just go to there and see. So you'll suppose you are using that kind of ductile damage model, GTN model. So this is what you will give. Then the subroutine. I am taking time for the material because material properties is something very important, because if you put a wrong input as a part of the material property, because the complex application there are so many properties which you have to give. So if you put wrong input for your material property, then there is a problem that you may get, you will not get the correct
Your voice is
result.
not clear.
Then you'll have the porous failure criteria. There you can see total volume, void volume fraction, which was over there as a BF. And then you have the critical void volume fraction, which is there as part of FC in that simulation formula. And then you have the void nucleation. So you can see that in the void nucleation, the mean and the standard deviation and the volume fraction. So Sn, Mn, Sn and epsilon and all these things I have told you. Okay. So these are the properties. Similarly, okay, echo might be coming because someone else mic is on. So that's why the echo, it might be echoing. Okay. So now let us see the third one is, so there are so many properties, we'll see the top three only. So now here you can see there are different models. You can see Johnson Cook model, FLD damage model, MK damage model. MK is Marciniak Kuznowski. FLD is forming limit diagram damage model, FLD base. Then FLSD forming limit stress diagram damage based model. So all these things you can see there are shear damage model, then you have the Johnson Cook model. So let us just open one diagram, and you see this is a FLD damage model. Here you have to give the strains, axial and horizontal, horizontal and vertical strain in any model which you will get from the 10 experimental values. So these are all the part of your mechanical properties. Then you'll have the Johnson Cook damage model. Here you can see different properties are there for the Johnson Cook model, which melting temperature, reference strain rate, which you'll have to calculate experimentally as a part of that material, and then you can put that and all. Now coming back to the thermal property. So thermal property, you can see all that conductivity, heat generation. So no, you don't have to give all properties everywhere. If we are doing a room temperature simulation where there is no heat involved and nothing, then there is no need for the thermal properties. Similarly, if there are electric, magnetic, piezoelectric properties and all these kind of properties, but we will only we will only restrict ourselves to the mechanical properties, because this is what we are doing. And then you'll have other properties, acoustic medium, and also the point which I am trying to explain here is that there's so much different kind of properties. Now, so I'm not assigned the material here because I have not given the properties. I have just explained to you all these things, right? So now once you'll do the property part, then you'll go to, let me just one more part is there. We'll come back to see when we'll see one example, one small example. So we'll do the meshing. Okay. So meshing of the part, let us just go to the part now. So this is the section is page. Okay. So now let us just see this. This is the seed part. This is for meshing. This is seed edges. Then this is mesh part. So you'll click here. Okay to mesh the part. Yes. Now you can see this part has become mesh. Okay. Then you'll have assign mesh control. So now you have to assign the mesh control. Okay. So what kind of element, what kind of shape we are doing. So before that, we'll see it later. First of all, let us assign the element type. Now we'll assign what kind of element we are going to use. So you can see there are many elements, three-dimensional stress, acoustic, cohesive model for pressure. So it depends what kind of application you are doing. So in the tensile test, you will have simple, let me suppose you are doing the tensile test. So you can select a simple, not the explicit one. Explicit and quadratic will not select. In the tensile test, you can select a simple 3D stress part, and then you can do it. So you can see over here that you have the standard linear. You have selected here. You can see a 4-node linear tetrahedron. So that is a 4-node model. Similarly, if you look at the quadratic, so that becomes a 10-node model. So let us just click on OK, and then it will be a 10-node model. So this is what we'll do. So we will not select that. Okay. So many things are there in the mesh control. So now let us go to this. I think assign mesh control is done. So first of all, let us do the seed part. So now you can see what is the approximate global size 1. So you'll have the overall global size initially we have chosen is this. So let us just try to increase this and see what happens. Let us just put it 1. Okay, 10. Now you can see this is here and here. Okay, so you can see only 4 points are mesh. This means this is a too big a mesh size. Our sample, our geometry is not that big that it can do approximately 10 global size. It can accept that. So now let us try to decrease it and see what happens. So now you can see 5. When I have done 5, now what it will do is that if we'll select it as mesh, it will, now you can see previous one, you can see how it was looking. Now you can see how it is looking. So when the analysis will happen only on this part, then this part, this part, this part, this part. So suppose this distance is suppose 20 mm, and we want the analysis on this part also, this part here, 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 and here. Means in the surface it will here, 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 and here. Suppose we want the analysis at all these 4 parts. So the analysis will not show it. So what we'll do is that this is very, very important. We again do the this seed control and we'll reduce its result. Now we'll do it to 3 and we'll see. Now you can see this is more part. Now let's do OK. And now let us assign the mesh. Now you can see it has become more refined. So now let us just go and do it more. Let's see how it's showing. Delete mesh 1. Let us do it more smaller and more final. 1 पे आपने देखा था, 1 पे you have already seen. Let's just show you how it looks at 1. Now you see this looks like 1, means it is going how many in the whole section, how many element it is going to give us. 1 2 3 4 5 6 7 8 9 10. 1 2 3 1 2 3 4 5. So total 50 points, 50 elements it is going to give us the result, unlike in 10 where in the top you are going to get. So that is what finite element is. This whole part you are dividing into finite number of elements. So I guess now you understand that from where the name of this particular subject came, finite element. So the whole part you are dividing, and this is what we call discretization. If you remember what we have done in the morning lecture, so I have talked about discretization and mathematical discretization. So this is what the discretization is, and this is what we as an engineer is doing. Once we'll assign all the property, what the software is going to do is going to do the mathematical calculations. which are already fit into the software, then only the software is done. So some other engineers have already done that. So that is something which we as a finite element engineers, we don't really need to do that, because this is for the development of the software. Okay, now come back to it. So again, let us just do it even a smaller, 0.25. Okay, we are doing the mesh size, delete the mesh. You can see at very small distance, you can see now the point. And when you'll see the mesh, you will understand. Now see the difference. Now see the difference. Now what is the difference between this one and the previous one? If we are going to do this, maybe it is going to give you a very final details very close to it. But the question for an engineer is, the question for the finite element simulation engineer is that whether we want so close, because now you can see the number of, let me verify it. Okay, let us verify the mesh. Select the region to be verified. Let us select the whole region. Done. Shape matrix and everything, highlight. Okay, dismiss. You see over here what you are getting. This is the critical point. This is a critical number. Number of elements is 64,200. 64,200 is the number of elements. Now, for each element, as I said, that the software is going to calculate what? The software is going to calculate the mathematical formulations, on the basis of which software is going to give you the generate the result. So for each element, the software is going to calculate the your overall calculation will be done for each element. 64,200 element the software is going to calculate. It is going to take a lot of time depending on the application. So whether it really required. So now you as an engineer have to decide that how much element we want. So let us just make it to 1. Okay, and let us do the same procedure again. Apply, okay, select, yes, this is the mesh. And now let us just go to the verify part. And now you can see this 945 elements. You can see over here 64,200 elements. So just try to understand that in a mathematical term, 64,200 divided by 945. What is the significance of it? So you can speed up your simulation 67 times. So if a particular simulation with this kind of meshing takes 1 hour, then the same simulation with the previous kind of meshing where we have 64,200 element is going to take 67 hours. Imagine. Means you are putting a simulation now and you are going to get the simulation done after 67 hours. Suppose if this simulation takes 1 hour. Okay. So how much time it's going to take? 3 days. And then there are certain simulations which for this kind of mesh will take 1 day. Yes, there are simulations. Industries may, factories may, it happens. Even for my PhD, it used to happen that we used to go to our lab. I used to put the simulation running, and then I used to go and sleep, and then I used to come next day in the evening, and then the simulation is coming towards the end. So yes, there are simulation which takes 1 day, 2 days, 3 days for the normal setting. So if we'll have so much finer mesh, imagine a simulation which is going to take 1 day for this kind of setting, and then you have the previous kind of setting where there is 64,200 simulation. The simulation is going to take 67 days. Who is going to wait? Are the companies, are the people in the industry, are the people who is doing the research, are they going to wait for single simulation for 3 days, sorry, 2.5 months? 67 days? No. So that is why this particular part becomes very critical. This is a decision of an engineer. Nobody will decide for you. If you are an engineer, if you are doing your project, if you are doing your research, if you are doing a simulation, nobody is going to decide for you that how much you want. Yes, there are senior people, there are senior executives, there are people who have the experience for it. So that's why, if you remember in the previous PPT, I've talked about the mesh sensitivity analysis. So again, this is a very important part for you to teach. Okay, so the mesh part now is already completed, uh, almost completed. Let me see if there are anything else for you to tell. Then you'll have the optimization part. Okay, so optimization part here, you'll have to see. Let me see what kind of optimization are there, because we have not made a complete part, right? So we have not made the complete part, so uh, nothing will come over here. Okay, we have not made the part, so nothing will come. But then there are optimization strategy, topology optimization, and everything. You will, once you'll made the part, you will define the material, you will do everything for it. Then, and the interaction, boundary condition, and everything. Then your optimization part will come, and then it will select the. It will ask you to select the material, the features where you have to do the optimization. Then you have the job. This is where nothing will come again, because we have not prepared the job right now. We have not given the boundary condition, everything. So we are just seeing the interface. So example we'll do after this. And then we have the visualization. So in the visualization part, you can see all these kind of results are there. Let me just, so this is a plot and deform shape. This is a uh, contour shape. Then you have, so what is a contour shape? That this kind of shape will come from there. So that's contour shape, you already know. The picture which is showing different kind of colors and everything. Okay. So you can see there is no output database. So we have not run the simulation. So then when there is no output database, it cannot show this for anyone. But, and this is a part of your result. Now you can see from the model to the result we have got. So that's why it's showing wherever you will click, it will come no output, because we have not yet done the simulation.